Learning partial discharge standards for testing of stator windings. And hopefully in the next 25 minutes or so, I'm going to touch on briefly some of the key standards that pertain to the partial discharge testing of stator windings and maybe clear up a few misconceptions about these standards. So in terms of what we're going to run through this morning, partial discharge analysis is used to evaluate the quality and condition of rotating machine stator winding insulation. So what we're going to cover this morning is what is partial discharge and how is it detected, the different types of partial discharge, and in this sense this is a discussion about the specifics of partial discharge mechanisms as they affect the deterioration of stator winding insulation, when and why one would want to apply a partial discharge test, briefly cover off the differences between offline and online partial discharge testing, and then we'll touch on some of the key industry standards, principally IEEE and IEC standards, and then we'll wrap up in about 20 to 25 minutes time. So what is partial discharge? It's basically the electrical breakdown of a gas within or on a surface of stator insulation. So basically, a discharge can only occur in the gas phase. It does not occur in the solid or liquid phase. So stator winding partial discharge, there has to be basically a gaseous void involved, whether that's in air-cooled machines or in hydrogen-cooled machines. Some of the common potential causes of partial discharge in rotating machines include surface contamination and insufficient electrical clearance, and these affect largely the end winding region of rotating machines. In addition, there's delamination, thermal aging, the bulk, winding insulation, loose windings in the slot, and there's stress grading and semicon degradation. The semicon is the resistive coating used the slot portion of the stator winding to positively connect the surface of the stator bar to the core iron. The asterisk that you see on this slide indicates that these issues are less likely or probable in hydrogen-cooled machines. So how PD is detected, and the slide here shows basically more a setup really for an offline partial discharge test. So we have a stator winding under test. In this particular case, it looks as if they're energizing the B phase. So we have partial discharge, I would assume coming from the stator winding. The PD is detected using a coupling capacitor, and the coupling capacitor provides two functions: to detect the high-frequency signals associated with partial discharge current pulse, and also to block the high-voltage power frequency signal. There will be a measuring impedance which basically converts the current pulse to a voltage pulse, and then either some form of commercial instrument will allow us to perform a so-called phase-resolved partial discharge measurement, or at least count the PD pulses, or if for those that are involved in research and development, observing the PD pulses on an oscilloscope. So when and why would one be doing a partial discharge test, whether it be offline or online? And there's two perspectives here. From the manufacturing perspective, they're doing this kind of testing, usually on both in coils and windings for factory acceptance, qualification, or development purposes. For the end user, typically these tests, if it's a new winding, they're obtaining the PD measurements as a baseline, and then thereafter doing periodic testing or monitoring to track the condition of the insulation over the years of service and it has to be said that partial discharge testing is best used in a trending mode. So in terms of what an offline partial discharge test looks like, this is a fairly standard diagram of what we're dealing with here. The assumption is that we're driving the winding with an external power frequency source. We energize the winding up to, or the coils or bars up to typically the rated line to ground voltage of the machine. So with that in numbers, for 13.8 kV machine, this would mean the test voltage would be 8 kV. Or in many cases, especially for manufacturers, they would perform tests usually up to the rated line-to-line voltage of the machine. In addition to recording the maximum partial discharge magnitude at the line-to-ground voltage, usually one also records the partial discharge inception and extinction voltages. And these are the voltages at which you first see the onset of partial discharge. That's the inception voltage, and the extinction voltage is basically the voltage at which you no longer see or observe partial discharge. There's two modes of doing this test, and typically both would be done assuming that it's practical and you have time. You can isolate PD sources by energizing all the phases together and then doing it one phase at a time. That way you introduce a somewhat different electrical stress configuration. And you can locate, if one finds partial discharge from these tests, you can locate the source of the PD with a blackout test, with an ultraviolet camera or a so-called corona camera. So this is visually observing the corona or surface partial discharge. You can use a TVA probe or some other radio frequency probe to probe the bulk of the stator winding insulation, or you can use an ultrasonic microphone.
Howard, we have a question.
Okay.
Is partial discharge measure or test a factory test that customers should do, ask, require every time? So it sounds like, is this a factory test that customers should require or ask for?
I would, if I was writing a specification, then in that specification I would require a partial discharge test at least at the stage before the stator winding leaves the factory. In many cases, many manufacturers actually perform partial discharge testing is on each individual bar or coil in the production phase. So manufacturers tend to do this. They may or may not disclose the results to the customer, but if I'm writing a specification, then yes, be requiring some form of partial discharge testing, whereas on individual coils, bars, or on the complete assembled stator winding.
Great, thank you.
You're welcome. So turning now to online partial discharge testing, and this assumes that some type of partial discharge sensor has been installed on or close to the stator winding before the machine is put in service. The advantage of online partial discharge testing is that you're observing the partial discharge under the operating conditions. So in other words, you have the correct voltage or the electrical stress distribution in the winding, the mechanical forces are present, and also the stator winding is up at its normal operating temperature. These tests can be done either periodically, so basically doing the test maybe once every 6 months or once every year with a portable instrument, or they may be automated for continuous or frequent monitoring with relatively little disruption to operations. Turning now to industry standards. The principle of partial discharge testing is not new. Some form of offline partial discharge testing, whether it be on individual coils, bars, or complete stator windings, has been around since at least the 1930s, as far as what we can see in the public domain literature. With respect to online partial discharge testing, this dates from about the specifically Westinghouse in the United States was definitely performing online partial discharge testing as early as 1949, 1950. And then in the mid-1950s, a utility called Ontario Hydro started routinely doing online partial discharge testing. So because there's approximately, in this case, a 60-year history of doing online PD tests and an 80-year history of doing offline partial discharge testing, there's been a number of different technologies that have been developed by various organizations. So the standards, as you see them today, are permissive of several different test methods, and you'll see those mentioned in those standards. What you won't see in any of these standards is any pass-fail or acceptance criteria based on a partial discharge test for stator coils or windings. And this is somewhat different to the situation for other apparatus or other electrical equipment, such as cables, switchgear, and transformers.
Howard, sorry to interrupt. We have a couple more questions.
Sure thing.
What equipment do you suggest for collecting the data from online testing sensors? What are you looking for specifically?
Well, I mean, obviously there's many commercial implementations. I think when you're doing online testing, one of the biggest challenges is separating the partial discharge signals from the stator winding you're interested in from the electrical noise or background interference that may cause you problems interpreting the data. So basically, you would look for a technology which provides a means of reliably separating the partial discharge from the noise. Because if you're unsure about whether you're looking at PD or noise, then interpretation of your data becomes very, very, very difficult. So that would be the key thing for me.
Okay. There's another question. How effective is offline PD testing and IES condition monitoring for in-service failure risk when PD activity is influenced by parameters such as normal operating temps, pressure, and loading?
That's a very good question. I think that there are offline methods tend to be used in many cases actually is you're doing offline testing often as a result of the results. You see something in the online test, and very often you're using an offline test to verify this. And also, usually as part of offline testing, there is some aspect of visual inspection, which has to be said, visual inspection is almost to me the gold standard, because you can't really argue with the evidence of your own two eyes. There are several deterioration mechanisms that you will not detect using an offline test. For example, if you think you have a loose winding, then for sure you need bar forces to basically drive vibration. So you will not see evidence of a loose winding from an offline partial discharge test. Where offline partial discharge tests are valuable is to say in verification of the online, but also if you couple the offline partial discharge test with a location test, such as, for example, a TVA probe test.
Okay, and then what about load condition during online PD test? Do they affect active PD activities?
If in terms of load effects, if you have a loose winding, then there is a correlation between loading and partial discharge magnitudes. And typically, the correlation is that as load is increased, if the winding is loose, then you'll see an increase in partial discharge magnitudes. This has been documented in several papers in the public domain since the 1980s. So if in the basis of your partial discharge measurements, see a predominance of positive polarity pulses over negative, and you suspect you have a loose winding, one way of testing for this with an online test is to modulate the loads, and typically you need to shift the load by approximately 40%, to be sure of the result. Is that okay?
Yes, that's great. We have two more.
Sure.
Of what significance is partial discharge inception and extinction?
In terms of for me, they are important parameters to record if you're doing an offline test. In principle, as a rule of thumb, and this isn't in any standard, so in some ways don't quote me on this. But typically, if the partial discharge extinction voltage is below something like approximately 50% of the rated line to ground voltage of the winding, then that usually means the stator winding insulation is not the greatest. Also, if you're performing something like a TVA probe test in conjunction with your offline test, recording the partial discharge extinction voltage and then using the information from a winding diagram will tell you whether or not a high TVA probe reading specific slot locations are less of a problem, because in other words, you can figure out from the winding position if that coil or bar is in a slot that's likely to be discharging in service.
Okay, and then can you quickly expand on the fact that there's no pass or fail for PD monitoring? If an online PDM is being performed, is there no way to tell deterioration is imminent?
Well, what the partial discharge test is telling you that deterioration is taking place, and by trending the data, you can see if that aging is progressing in a manner that would concern you. Unfortunately, there is no way of correlating partial discharge magnitude with so-called insulation remaining life. What you're really using partial discharge monitoring for is basically to indicate whether or not maintenance or some other form of action is required in that stator winding. So you can trend the data if you have access to a database, which basically we've been building in IRIS for many years. We're able to relate the Qmax, or the maximum partial discharge magnitude, to machine condition through a statistical database, but that's based on things like voltage class, gas pressure as a hydrogen-cooled machine, and the type of sensor installation.
Do you have
just to go back to the pass-fail criteria, there tend to be none, because first of all, there's a number of different ways of doing partial discharge testing, which can affect the partial discharge magnitude. And any technical committee I've ever been involved in that arena, it's a very unpopular topic for certain organizations in terms of introducing, pass-fail or acceptance criteria based on partial discharge.
And just to clarify, for trending a value, are you specifically talking about vibration or temperature, or both?
Basically, when the partial discharge data is analyzed, the interpretation looks at all of these aspects. If you're using partial discharge in the trending mode, what typically, and this is for online PD testing, what ideally what you would like to have is that every time you do the test, the machine operating conditions are pretty much the same, and the IEEE and IEC standards actually define what the tolerances are for machine operating conditions. So all of these factors are taken into account: loading condition, winding temperature, fluctuations in the terminal voltage, hydrogen gas pressure, and also humidity in air-cooled machines are all factored in when one is analyzing or trying to interpret the partial discharge data.
Do you happen to know, Howard, if there's a bad rate of increase or what level someone should be concerned and recommend an intervention?
Well, I can only truly speak for measurements made with iris-based equipment, but typically a rapid rate of deterioration for us would be where you see the maximum partial discharge magnitude, whether it's positive or negative, doubling over a 6-month to 1-year period. If you see a doubling of the PD magnitudes in that kind of time frame, that would define for us rapid deterioration.
Okay, great.
Okay, so I'll continue on.
Mm-hmm.
Okay, so looking at going back to the standards now, one of the first recognized consensus standards was ASTM D1868, and that's the American Society for Testing Materials. This is a standard that's principally used for lab and factory-based testing. But one of the most well-known standards is the IEC 60270, and it's very widely used and also very widely quoted. This standard is really only truly valid for capacitive test objects. The original IEC 270, actually, the footnote which said don't use this for inductive-based equipment, which is a large stator winding. But the latest generation has removed that footnote. So where in IEC, because things tend to sort of follow along in a very regimented fashion, IEC 634-27, which is for partial discharge, offline partial discharge testing of coil bars and stator windings, they base their methods solely on IEC 6270. And for winding, for stator windings, the problem is that 6270, you have to calibrate the PD current pulse in picocoulombs. And that is not either easy or in some cases possible for large stator windings. Picocoulomb, just to define it, is a charge quantity. And basically, the higher the picocoulomb level or charge, then that's giving an indication of how much potential damage you're doing with the partial discharge as it impinges on organic insulation. So this next slide just shows the basics of a PD measurements, an offline partial discharge measurement according to IEC. You have a high voltage power supply, the test object, some form of measuring or blocking capacitor, that's CK, and a measuring impedance, which in Europe they call a quadrupole, and some form of IEC 6270 compliant measuring instrument. Or from a practical perspective, the 6270 methods, which are intended for capacitive test objects, are good for making standard repeatable measurements in lab environments where the noise can be controlled or excluded. It's not so easy when you're in the field testing the entire stator winding. And also IEC 634-27, as I've mentioned before, along with other test standards, does not specify a maximum partial discharge magnitude at the rated line to ground voltage, which is considered good or bad or indifferent. So some organizations have suggested 100 picocoulombs, but to date, that's gone pretty much nowhere.
Howard, is for the ASTM standard, is there an equivalent to Europe except IEC?
Not that I'm aware of. I mean, in Europe, you'll have individual countries will have their own national standards. But I'm not aware that there'd be a sort of an equivalent to the ASTM standard. The ASTM standard is quite similar to sort of like an IEC 60270 procedure.
Okay, great.
So continuing on, with standard test methods with respect to offline partial discharge testing, IEEE 1434, which actually covers both online and offline testing, is the IEEE equivalent of IEC 634-27. 27 only covers offline PD test methods. And so what's covered in those standards are things like test setups, the acquisition frequency range, or basically the frequency range of the measuring instrument that you're using. IEEE permits any and all frequency ranges. The IEC standards is very restrictive, basically between 10 kilohertz and 1 megahertz, which is basically done to keep it consistent with IEC 60270. It provides procedures for attaining the peak partial discharge magnitude, or the so-called Qmax or QM, the partial discharge inception voltage, PDIV, and the extinction voltage, or the PDEV. Or the point which is never, or at least the debate which still rages today, is basically how to calibrate the Qmax into picocoulombs on now a test object which not only has capacitance but also inductance. So, coming to this point about acceptance criteria, there are still no hard pass-fail PD limits for new machines. Some organizations, some end users impose their own. Manufacturers, they have their own internal procedures. Very often this is a comparison with their database for similar stator designs, and assuming that they're using exactly the same test instruments and methods. And there's many difficulties because of differences in the insulation materials, the construction, and the geometry of stator winding. All of these can have a profound influence on your PD test results. So there are other offline methods to look at partial discharge and stator coils and windings. One of them is IEEE 1799, which is a relatively recent document. And what this document does is it formalizes the blackout test and also the use of ultraviolet or so-called corona cameras. And in this case, what they're looking for really is surface corona and corona that's occurring in and around the end windings. You're using this as a quality assessment method of the interface between the semicon and the stress grading materials, and also the clearances in the end winding. Online PD testing is covered under IEEE 1434 and IEC 634-27-2. In this case, the range of frequencies extends from 3 megahertz up to 3 gigahertz, and both standards are very comprehensive and permissive of many different test methods and instruments. At the higher frequencies, because we go from relatively low frequency in the HF range up to the UHF range, with higher frequencies, as you go higher in frequency, the advantage is that you see basically that it's done for signal to noise ratio reasons. At high frequency, it's easier to distinguish the partial discharge from the noise. However, the downside is that these instruments operate at higher frequencies, will in principle see less of the windings. So there may be the higher frequency instruments are maybe only seeing the first 1 or 2 coils or bars from the line end position, although of course it's dependent upon where you install the PD sensor. In terms of interpreting, as I mentioned before, the optimum method for doing or trying to make sense of partial discharge measurements is in the trending mode. And so basically doing regular testing with a uniform test method approximately every 6 months to 1 year. Depending upon what you're seeing, you may shorten up or lengthen that test frequency, but usually at least once a year. And if it's relatively easy to do, then we'd suggest that we're doing it every 6 months. Another way of doing this is if you have a database which we do an iris of something like 450,000 test points, then you can compare PD magnitudes to a database for measurements from similar machines, and these are similar machines. This is when we group by voltage rating, hydrogen pressure, assuming it's a hydrogen cold machine, and the test method. In this case, the test method means the specific types of sensors that we've installed. As a follow-up to the, in order to get better insight into your interpretation, then if there is elevated partial discharge being observed, then usually one would follow this up with visual inspections and other types of diagnostic techniques before making any further decisions on maintenance, repair, or replacement of winding components. So just looking at a couple of examples of, then this is from an online partial discharge measurement. On the screen you see basically on the y-axis is the pulse magnitude in millivolts, the x-axis is the phase angle, because this is a phase resolve measurement. You can see a display of the power frequency sine wave, and the number of pulses per second is denoted, it's color-coded according to how often the pulses are occurring per second. This is an example of classic partial discharge in the bulk of the insulation in the slots. We can tell this by the fact that the positive and negative partial discharge distributions are centered around the 45 and 225 degree phase positions, and that the magnitudes are roughly equal between positive and negative. Turning now to, this is an example of partial discharge occurring in the end winding. Specifically, it's occurring between two different phase bars in the end windings. This is interphasal PD, and what's characteristic here is that we basically shifted by approximately 30 degrees from the previous slide, which showed slot partial discharge. And really, it's being able to distinguish between partial discharge in the end winding and partial discharge in the slot is fairly important if you're trying to guide maintenance planning on the basis of partial discharge measurements. And just to briefly compare IEEE and IEC standards, you will see just one of the things maybe to take away from this slide is that the IEEE standards tend to be more permissive than the IEC standards, although the online, the comparison between the online standards shows that pretty much IEC and IEEE are in line with one another. You'll note that the number of online PD test methods permitted under IEEE is 12, and those under IEC is 5. And in IEEE, there tends to be, as I say, the standards tend to be more permissive of any and all technologies, assuming, of course, that they're valid technologies. And just the bottom line here is that there are absolutely no acceptance criteria for either coils, bars, or stator windings. So in conclusion, PD testing, whether it's offline or online, is very widely used pretty much worldwide by both end users and manufacturers. There are many independently developed technologies available to acquire and analyze the data. International standards in IEEE and IEC have been developed to permit a number of these test methods and a number of measurement frequencies, but the bottom line here is that there are still no industry acceptance limits for partial discharge magnitude, inception, or extinction voltages. And this is unlike the situation for other types of power apparatus. And at this point, I will conclude speaking, and if there are any further questions, I'll be happy to attempt to field them. Thank you very much.
Thank you so much, Howard. We have a bunch of questions. The first is, do you recommend online PD monitoring for new stators? If yes, what is the advantage?
Well, first of all, the answer is yes. And the reason why I would recommend doing that is that it basically, in fact, whether it be doing offline or online testing, I'd recommend it for a new stator winding, because that's the point where you'll get your baseline. Because it's very key to the baseline in terms of interpreting what's happening with your stator winding as you go out in time over a number of years of service. One of the points that I'd like to emphasize is that when you take the first online measurements on the new stator winding, if it's done very soon after commissioning, that perhaps you might find that the numbers may be a little bit higher than you'd expect. But then the thing here to do is to do a further test maybe 6 months after, and you may well find that the PD values have come down, and there's a number of reasons why that may occur. One of them is that in the new stator winding, sometimes the winding takes time to basically bed down or conform properly with the slot. So for sure, I think I would for sure recommend installing equipment or doing online testing on a new stator winding.
Okay. Is SSC sensor ever have failure that affects the running motor? By
SSC, I guess this is a stator slot coupler, and these would be installed usually in large turbine generators. So I'd have to say, not to my knowledge, in terms of have there been problems with machine integrity. The key thing with the SSC is the SSC itself sits in the slot, so it's not going to be a problem. The key thing with an SSC installation is to make sure that the leads that run from the SSC are properly located, and by that I mean they're basically affixed to grounded structures and not left hanging over the high voltage stator bar or across the end winding.
Okay. If PD testing is not pass-fail, how is testing evaluated on new bars, coils, and stator assemblies in the factory?
in the factory, the manufacturers, in some cases, if you have a very let's call it proactive end user, they will have been very insistent on telling the manufacturer what the pass-fail criteria are. In general, though, the manufacturers, in my experience, they have, if they're doing PD testing and they're doing it on a batch production basis, they will make the measurements. They will have a database, and typically one way of deciding what they're going to accept or reject will be to look at the average, and then see what's maybe 3 standard deviations away from the average. But it's not a hard number. It's on the basis of what the manufacturers are measuring on their products over a period of months, years, maybe even decades. Pretty much know what to expect, and they will analyze the data statistically to make sure that they're still, falling within, the normal standard deviations.
Okay. How does the seventh coupler suggested arrangement allow you to see PD further inside the winding?
Sorry, was that seventh coupler?
Yes, seventh.
Okay, I think I have to assume that this is relating to an SSC installation. If not, I apologize, but I mean, in one case, if you're looking at the phenomenon of vibration sparking, and vibration sparking is a mechanism which can actually occur anywhere in the stator winding. So therefore, couplers, high-frequency couplers installed at the terminals of the stator winding will probably not see anything that's occurring further into the stator winding. And so therefore, installing another coupler at basically or close to the neutral position is a way of basically seeing a little bit further into the winding. So that, and I apologize if I'm misunderstanding the question.
Nope, that's okay. There are different sensitivity ranges in PD software. Should we collect data on all the sensitivity at each phase, or are there specific ranges in which PD occurs?
What we'd suggest, and I believe this is probably in the manual that accompany our PDA and TGA equipment, is it typically if it's the first measurement you're doing on that particular stator winding, we'd suggest using one of the mid-range settings, say maybe the 20 to 340 millivolt, and then seeing what kind of result you get from that. the key thing is to look for what the quality flags are telling you. If the quality, the key one is the OVR or over. If you see that quality flag set after the conclusion of the measurement, then you should move up to the next sensitivity range. In this case, I'm meaning the next least sensitive sensitivity range. So, for example, if you get that quality flag on 20 to 340 millivolts sensitivity setting, then the recommendation is to move to the 50 to 850 millivolt setting, and then see if that clears a quality flag. So basically, you want to keep doing the test until the quality flag is clear. There's no need to perform basically to use every sensitivity setting on every measurement. And as the next time you go and make the measurements, it becomes somewhat easier because now you at least have a sort of a feel for where you should be setting that sensitivity setting.
Okay, great. How does ending winding vibration correlate with end winding PD?
I'd have to say it doesn't. If partial discharge testing will not per se detect end winding vibration. In order to find end winding vibration, you actually need to use a dedicated end winding vibration monitoring system. In terms of end winding partial discharge, either due to contamination or insufficient phase clearance, normally the winding would not be, that partial discharge phenomenon that we're seeing as interphasal or resulting from contamination, we don't believe would be modulated by the presence of end winding vibration.
Okay. Let's see. Could you explain the logistics of an online test, the coupler placement, for example?
Well, typically, if this is on a motor or a small turbine generator, typically in this case you're using a so-called bus configuration, using basically a time of arrival technique. So there would be you would try to get the so-called machine side couplers installed as close as you can to the machine terminals, and sometimes that's easier or harder depending upon the placement of configuration of the bus, space inside terminal boxes, issues with CTs or surge arresters, and then the system side coupler should be installed at least 2 meters or 7 feet away from that machine side coupler. Often, again, there are constraints as to where that system side coupler can be installed. So the 7 feet is really the minimum distance. It can, in fact, be further out than that. As far as, so basically with bus installs, you want to get the machine side coupler as close as you can to the terminals. On differential installs, which are really more germane to hydro generators, you're trying to get both couplers C1 and C2 as close as you can on the circuit ring bus to basically the exit of a line end coil from one of the circuits in the winding.
Okay. How long does it take for a new machine to settle?
I guess without trying to be too facetious, it's a bit like, you know, asking how long is a piece of string. Typically, though, in my experience, and everybody's experience is always different, usually 6 months to 1 year. I've seen sort of like interesting results that have taken like a year to settle down. If you know, if it goes the other way and you see sort of like high readings and then readings become higher, that's an altogether different problem. But typically, if you take a, you know, a measurement after commissioning 6 months in and then 6 months beyond that, it should be settling down at that point. Otherwise, it's basically it's going to be what it is in terms of like that those are higher magnitudes. But 6 months to a year is a rule of thumb.
Okay. Do you recommend continuous online monitoring versus portable with 6 months frequency on a new machine?
It sort of depends. There are many reasons why end users go either continuous online system or portable. If your plants are easily accessible, then probably portable instruments is the way to go. In some cases, some of our end users are plants in very remote locations, so it's much more convenient for them to use basically a system that's continuously monitoring and also they're able to interrogate it. If you're into, say for example, one case perhaps if you have critical motors, because motors may require a bit more monitoring than large turbine generators, then maybe you might want some form of continuous online monitoring for them. But there's no, every situation I believe is different, and it has to be looked at on a sort of a case-by-case basis in terms of what the end user was trying to, it was basically what kind of value they were trying to extract.
Okay. Is there a way to eliminate noise in the test using only the software?
That's an interesting question. Because the way that the IRIS equipment works is that basically the PD is separated from the noise, actually either the coupling method or in the instrument itself. So in terms of the question is, we could need post-processing done. The simple answer is no, because once we have the data, we can I shouldn't say no, because what we can do, because all IRIS instruments, though they separate PD from noise, all of the data is retained. So you can go back in after the fact into the raw data and look at the partial discharge. You can also look at the noise. So everything is kept. So if you have some suspicion that there's something not quite right happening, you can go in after the fact and analyze all of it. There is no specific software per se to do that. So as I say, all of the algorithms are embedded in the coupling schemes and in the front end of the instruments, basically using you know, high frequency characteristics, impedance mismatches, looking at where the signal is occurring with respect to the power frequency phase position, and we also analyze the pulse shape. But by the time you see the data, it's been done for you, it's transferred.
Okay. Is there a limit on the size of the motor where PD becomes ineffective?
In terms, I guess to me it's not so much size, it's voltage class, which is maybe what the question refers to, and if it's not, I apologize for misunderstanding. in some cases, there's very often people will say, for example, on 4 kV motors, that there's no point in trying to measure PD because there is none. And that's not actually a true statement, because it's not voltage that drives partial discharge, it's electrical stress that does. And in my experience, there's plenty of partial discharge on 4 kV motors. The question becomes is how often you should monitor, because as you go down in voltage class, the insulation will, and so therefore time between seeing partial discharge and something bad happening, the time frame is reducing. So it may be in the case of, oddly enough, with motors, you might want to monitor them more often than large turbine generators, which you get much higher insulation build and therefore more margin. But I don't think there's any limit on size other than in voltage class. Probably below 3.3 kV, I don't think it's worth your while doing PD monitoring.
Okay. Is there a working group who works specifically on how to evaluate stator winding health?
Not per se a working group that does that. For example, IEEE, there are many working groups that look at all the different test and diagnostic methods associated with rotating machines. So whether it's working groups on stator core testing, on stator windings, or at least on stator winding testing, where it's partial discharge, capacitance, dissipation factor, insulation resistance, the focus of all of these groups is stator winding health. But I don't think there is a specific IEEE working group or IEC working group that has been struck specifically to look at the whole more global issue of stator winding health.
Okay.
I'm always prepared to be wrong, because there's always some IEEE working group lurking around somewhere that I don't know anything about.
All right. What's your argumentation for online monitoring, since it looks like OEMs provide LEAP? Every customer wants to know the lifetime of this machine. The argumentation against it is to non-technical is very hard.
Okay, I didn't quite understand the question, Ellie, sorry.
That's okay. We can address that one offline.
Yeah, because I heard, I think I heard the term LEAP being used.
Yep. Yeah.
This is the certain OEMs' proprietary like life assessment methods. I think first of all, I'd agree that there's definitely a need to demystify basically how decisions or how assessments are arrived at. In terms of what we try to do with the IRIS equipment is basically have something for the end user can basically do the tests, and with relatively little training are able to interpret the results of the test. So basically, we only see approximately 30% of the test data coming back from our clients. The concept is to provide an instrument and a test methodology where the end user can basically do their own test and interpret their own test results. And we only see maybe 30% of the test results coming back from our clients. So I think maybe that indicates that there has been some demystifying, at least, of what's done in online PD testing. But I'm probably misunderstanding the question, and I'm happy to come back to that offline.
Sure. All the questions will be recorded, so we can address them offline when the webinar is finished. Of the different PD sensors on the market, including different capacitance couplers, how would you rank their effectiveness, reliability, and PD measurement?
Well, one of the things in terms of if we touch on the subject of reliability, one of the things that's topics that's contained in both the IEEE 1434 and and the IEC 634-27-2 documents is that they actually discuss what are the requirements for PD couplers that are going to be installed in the stator winding. And so if you're looking at the various providers in this market, perhaps one question to ask them is are their sensors compliant with either the IEEE or IEC standards? Because with what's embedded in those standards are basically all of the evaluation tests to make sure that sensor is safe to go in the unit, that it's been subjected to sufficient testing, whether it be voltage endurance, whether it be things like looking at tracking resistance, make sure that coupler is compatible with the integrity of your machine. Can you just repeat the question for me again, please, Haley? Just because I'm missing in a couple of points here.
Oh, I already archived it. I'm sorry. We have a few more to go through. We can address that one again offline. Since the coupling caps only cover about 10 to 15% of zone of sensitivity for the coils, are you looking to incorporate the installed stator RTDs with the caps to increase the zone of sensitivity?
So the simple answer to that is no. The reasoning, first of all, the reasoning behind why we don't get too concerned about the lack of, let's call it, stator winding coverage is because the sensors are installed at or close to the line end positions of the windings. In other words, where the highest voltage point in the winding. And so from the perspective that PD is a voltage and electric stress-based mechanism, the couplers are sitting in the region which has got the highest probability of partial discharge occurring. And over we first started doing installs of, when I worked for Ontario Hydro, installs of the PDA type technology with the 80 picofarad capacitive couplers. So that was about 40 years ago, and we never, to the best of my knowledge, I don't think we had too many false negatives. In other words, we didn't miss too much, and we didn't have any unexpected insulation failures. So that's kind of the rationale behind why the couplers and the high frequency angle. With respect to the other part of the question about RTDs or slot thermocouples, the RTDs measure temperature, they don't measure partial discharge. What you'll be seeing from an RTD is probably whatever has been coupled from the machine into the leads of the RTD, and that is going to be very difficult to figure out what's partial discharge from what's noise. So that's why we wouldn't in IRIS adopt that approach.
Okay. How concerned should one be if they see a large downward trend in the PD as opposed to a large upward trend?
Well, I guess it depends upon the where you are in terms of the age of the winding. If there's a downward trend on a new machine, and I guess large is a relative term here. If a downward trend in a new machine is something that's maybe not expected, but it's not unknown, and it's relatively common. A downward trend on a machine that's maybe 20, 25 years old, it is a concern, because perhaps what this is telling you is that the parts of the winding now have become either so carbonized that basically parts of the winding that used to be contributing to the partial discharge are no longer part of the equation, because the void surfaces have become carbonized such that they're no longer able to sustain any voltage. So a downward trend on an older machine, I'm not going to really put numbers on it, but definitely on a machine that's seen significant service would be a concern, and would need further consideration and potential maintenance actions.
Okay. Do PD tests contribute to aging or damaging of the coils or bars?
The the simple answer is no.
Okay.
And just from the perspective of, sometimes the question is asked a little bit of a different way in the sense, in the context of, do high POS, do over voltage tests harm the winding? And the answer is on basically good insulation, you're not going to be damaging it. So in terms of doing a PD test, if you're conducting the partial discharge test at the normal operating voltage of the winding, then basically you're not applying any additional stress. Basically what you're doing is you're seeing the symptoms of other deterioration mechanisms present anyway.
Okay. Let's see here. How important is it to monitor PD for gas insulated switchgear?
Well, yeah, again, very, very important. I guess we just sort of changed the subjects here. But certainly PD monitoring of GIS. I mean, it's been, there's a number of organizations in that business, and GIS PD monitoring has been around probably when I worked for Ontario Hydro, we had systems installed, and that was back in the early 1990s. So there's probably like a 25-year history of that, and very good experience from what I understand, although I'm not a GIS specialist. But certainly on high voltage, 230 kV and above GIS, then having some form of PD monitoring installed is probably a good idea.
Okay. Just two more questions. Sometimes we get measurements with OK quality flag, but after 1 year at the same sensitivity range, the quality flag shows warning. And now we move to another sensitivity range. Are we able to compare the new sensitivity range with the previous collected sensitivity range?
Yes. What if by warning, if what's happened is that the so-called OVR or over flag has been set, what it's telling you is that there may be partial discharge pulses above the current range setting that you have, and to shift to the next one. But you will still be able to, the two range settings will be compatible, so there will be, continuity between the two. So you're not invalidating the trend by shifting to another range setting.
Okay, and last question, why can't we decide the limits for PD magnitude, like transformers and instrument transformers and cables, etc.?
Well, I think there are technical reasons, and there's also let's call them commercial reasons. The technical reasons boil down to the fact that, and I think during the webinar we mentioned that there's a number of, each standard, whether it's IEC or IEEE, is permissive of a number of different methods of testing. IEC tries to, the 634-27 standard tries to impose 6270 on everything to try and give you uniformity. The problem is that 6270 isn't completely appropriate for stator winding testing. And so if to cut a long story short, if you take two instruments and apply them to the measurement on the same stator bar or coil, literally this apart, we'll get two different results, or more than likely two different results. And so therefore, try and sort of say that then X picocoulombs or Y millivolts, nobody right now is willing to accept that. And there's and obviously the manufacturers have their position, and the end users have theirs. Having been in the end user camp, I think there are actually practical ways forward. But trying to get consensus, which is normally what you require in standards making, is very difficult right now. Still with this confusion, so it's a matter that's still being studied. But unfortunately, unlike transformers and cables, there's still no consensus over this, and I'm not sure that we're going to solve this question of in the very near future, unfortunately. So it certainly holds back for me, the application of partial discharge testing, because there are no acceptance criteria.
Okay. All right. Well, that's all the questions that have been submitted so far. As I said earlier, the recording of the webinar and the presentation will be emailed to all the recipients sometime tomorrow. In addition, the questions have been recorded as well, so you'll receive both the PDF slides and the recording with the questions. So thank you so much for participating, Dr. Howard, and for everyone on the line as well. And stay tuned for our next webinar. Thank you so much.
Thank you.